where sight becomes story.
See better, shoot better, create better.
You got the camera, now get the vision. Shoot with purpose, create with vision.
Creative vision, creative vision.
This is Creative Vision, where sight becomes story.
Hello everyone, and welcome to our new tutorial series. Every photo you take starts with light. But what exactly is light? In this new tutorial series, we bridge the fascinating worlds of physics and visual arts.
And God said, "Let there be light." For humans, the entire universe could not function without light. We see and understand things because of light. Without it, our eyes cannot see objects. In fact, we humans couldn't survive without the sun's light. Light plays a crucial role in understanding the structure and properties of everything from atoms to the universe. This light raises many questions for humanity. Since ancient times, we have been trying to understand what light is. Light acts like a messenger of information. When it encounters an object, it reflects off that object, carrying information from it, then enters our eyes. Within a millionth of a second, our brain processes this information and helps us understand what we are seeing. Even though light is a messenger of information, it is itself invisible. That's why space appears so dark. We can only see the existence of light when it encounters an object. We see rays of sunlight because they pass through dust or gases. We already know that light travels at the incredible speed of around 300,000 kilometers per second and doesn't require any medium to travel. This is the maximum speed of our universe. It is a very special and unique property of light. Nothing else can travel at this speed. However, one of the greatest physicists of the 19th century, who worked on electricity and magnetism, predicted through his equations that light is just a part of radiation. Along with light, all radiation travels at the same speed. This radiation is called electromagnetic radiation, or electromagnetic waves. Electric and magnetic force. Every charged particle in our universe has an electric field. An electric field is simply a distribution of force or lines of force. Electric field lines are the simplest way to understand an electric field. First introduced by the father of electricity, Michael Faraday. Electrons have a negative charge, so they have an electric field, while protons have a positive charge and also have an electric field. However, the fields differ depending on the charge. For a positive point charge, the electric field lines radiate outward, while for negatively charged, the electric field lines radiate inward. A magnetic field. A magnet always has two poles, a north pole and a south pole. Magnetic field lines always start at the north pole and end of the south pole of the magnet. Like electric charges, similar magnetic poles repel each other, while opposite poles attract. The main difference between electric and magnetic fields is that in nature, negative and positive charges can occur independently of one another, whereas magnets always have two opposite poles. We have never found independent magnetic poles in nature with only North Pole or only South Pole. Even if a magnet is cut into two pieces, each piece becomes a new magnet with both a North and South Pole. No matter how many times we cut it, the pieces always have opposite poles. Simply put, the electric field originates at a positive charge and terminates at a negative charge. In the case of an isolated positive point charge, the electric field line starts at the charge and extends to infinity. For an isolated negative point charge, the electric field lines start at infinity and end at the negative charge. So, this field exists around the charge at all times, even if there are no other charged particles nearby. Although the range of an electric field may be infinite, the strength decreases with distance, meaning the field is stronger near the charge. The electric field is responsible for electric force, where like same charges repel each other and opposite charges attract. The field is always active. When two opposite charges come close together, the electric field of the positive charge links with the electric field of the negative charge. When two positive charges come close together, due to their similar outward fields, they repel each other. Magnetic forces were first observed in natural magnets. Similar to electric fields, magnets also have a field called a magnetic field.
Creative vision, where sight becomes story.
See better, shoot better, create better.
Electromagnetic force is a combination of electric force and magnetic force. But why do we combine them? Why can't they be separate forces?
Electrons are at the heart of light creation. Let's see how their motion generates the electric and magnetic fields that give rise to electromagnetic waves.
Creative vision, where sight becomes story.
Let's break down the electric field concept. An electric field is a region around a charged particle where another charged particle would experience a force. We often visualize these with field lines, which show the direction of the force a positive test charge would feel. In photography, electric fields are integral to the very creation and detection of light. When photons hit your camera sensor, they knock loose electrons, creating an electrical signal. This process is fundamentally about electric fields interacting with matter.
You can see if I place this rubber here, right here, nothing is happening. Nothing is happening. I'm going to rub this rubber against this 4. Can you see something? Some of them are running away. Some of them are actually running away. Look at them. They are moving. See? They are moving. Some of them are running away while others stick to the rod. So look at it again. You see? Because those ones have the same charge as the rod, they run away. But those ones that are opposite charge to the rod, they stick to the rod. So this is one way we can prove the existence of charge.
Creative vision, where sight becomes story.
See better, shoot better, create better.
You got the camera, now get the vision.
When you charge your 4, and take it close to the machine, what you find is that it displaces because of the charge that is transferred, the static charge that is transferred from the rod to the machine. And so if you are able to rub this enough, you just find out.
To visualize this better, I'll bring in a short demonstration from another video. Watch carefully as light strikes the metal surface and causes electrons to be emitted. This is the photoelectric effect in action. Today, we are going to see one of the most powerful ideas in the science of light, the photoelectric effect. This experiment shows us that light is not only a wave. Light can also behave like tiny packets of energy called photons. This device is called an electroscope. It helps us detect the presence of electric charge. When extra electrons are placed on the metal plate, the needle moves, giving us a visible sign that the plate is charged. When extra electrons are placed on the metal plate, they spread throughout the conducting material. The repulsive force between the charges makes the needle move, giving us a visible sign that the plate is charged. We can charge this device using simple static electricity. Let's see how it works. When a balloon is rubbed against fabric or hair, it can collect extra electrons through friction. The balloon now carries a negative static charge, packed with thousands of excess electrons. When those electrons are transferred to the electroscope plate upon contact, the charge flows into the instrument. The needle moves instantly. This shows that the plate now has a stable electric charge. Now we are going to test how light affects this charge. We'll start by shining visible light on the plate. This light is made of many wavelengths combined. It is a bright, high-intensity source. Even if the light is very bright, meaning there are many photons hitting the plate, the needle does not move back. The electrons remain attached. That is because each visible light photon does not have enough energy to knock them off. Despite the intensity of the light, the charge remains on the plate. The needle stays exactly where it is. But watch what happens when we switch to a higher frequency source, ultraviolet light. Something very different occurs now. Each ultraviolet photon carries more energy because of its higher frequency. When these high energy photons hit the metal, they can provide enough energy to knock electrons away from the plate. As the electrons are ejected, the total electric charge on the plate begins to dissipate. The needle returns toward neutral as the charge drains away. This is a direct physical result of light's particle behavior.
UV light. Can't I just use regular colors of light to get the photoelectric effect? Well, let's try it. Red, green, and blue. Even the long wave black light, ultraviolet, doesn't work. It has to be UVC, and that's what this special lamp is for.
Brightness is not the same as photon energy. A very bright, low-frequency light may contain many photons, but each photon may still not have enough energy. A higher frequency photon, like ultraviolet, can carry enough energy to release an electron. This is called the photoelectric effect. Intensity only changes how many electrons are released, but the frequency determines if they can be released at all. This threshold frequency is a fundamental property of the material and the physics of light itself. So remember, to knock an electron loose, you don't necessarily need more light. You need higher energy light. This entire process of light knocking electrons loose from a material is called the photoelectric effect. Light transfers its energy in discrete packets to the electrons. If that packet has enough energy, the electron is released. This discovery was revolutionary because it helped prove once and for all that light can behave like a stream of particles. At the microscopic level, it looks like a series of collisions, with each photon acting as an individual particle. The photoelectric effect changed our entire understanding of the physical world and the nature of energy. Light is fascinating because it behaves in two ways. In some experiments, it acts like a wave. In others, like this one, it acts like particles. It's as if the wave is made of these tiny pieces. This strange reality, where light exhibits both wave and particle properties, is what we call wave-particle duality. It's a cornerstone of quantum mechanics, showing that our universe is much more complex than it appears to the naked eye. Understanding this duality is the first step in mastering the science of imaging and modern technology. This same fundamental idea is what makes modern digital photography possible. It all starts with the sensor. Digital camera sensors are essentially millions of tiny photosites that are designed to respond to these photons. When light hits a photosite, it triggers the photoelectric effect, releasing electrons that produce a precise electrical signal. That electrical signal is then processed and converted into the digital image we see on our screens. Every photo you take is essentially a map of where photons landed and how much energy they carried. So, the photoelectric effect teaches us that light is not just something we see. It's a powerful carrier of energy. It carries that energy in tiny packets called photons, which interact with the matter around us in profound ways. These photons are the silent science behind modern cameras, digital imaging, and how we capture the visual world. Thanks for watching. I'm Michael Tasker, and this has been Creative Vision. Keep exploring the science of light.
Creative vision, where sight becomes story.
See better, shoot better, create better.
You got the camera, now get the vision.
Light is confusing. I've been talking about it as discrete particles, But then I say it has a frequency, the number of oscillations in a given time. How does a particle oscillate? To understand, we need to define what a particle actually is. The actual definition of a particle is the smallest possible vibration of a quantum field, and a photon is simply the smallest possible vibration of the electromagnetic field. That's how a particle still has a vibration. It's an underlying field manifesting as a particle. This is wave-particle duality, why light can appear as both a wave and a particle. Now, higher frequency particles, whether we talk about something as a wave or a particle, kind of depends on its wavelength or its frequency. The higher frequency particles, like ultraviolet light and X-rays, tend to always manifest themselves as particles. So we usually can't see the peaks and valleys of their waveform because they're too close together. So we usually call the higher frequency things particles. Whereas particles with lower frequency, we usually just always call them waves. For example, radio waves have an extremely long wavelength and a low frequency, so we usually only see their wave properties and never their particle properties. In fact, we've never even been able to detect a particle of radio waves because a single photon in the radio frequency has such low energy that we can't detect it.
Create a vision where sight becomes story.
See better, shoot better, create better.
You got the camera. Now get the vision.
The story of electromagnetism begins with the invention of the battery. In 1800, Alessandro Volta invented the battery, a device that pushes electrons from one place to another. This movement of electrons is known as electricity. An electron is a charged particle, so when a charged particle moves, it creates electricity. In 1820, Danish physicist Hans Christian conducted a famous experiment. He placed a compass near a current carrying wire. Naturally, a compass needle points in the direction of North and South Pole, direction of Earth. But when he placed near the current carrying wire, the needle deflected from its original direction. This demonstrated that the movement of charges produces magnetic effects, which is why the compass needle was deflected. However, a stationary charge, no matter how large, has no effect on a magnetic needle. A charge must be moving in order to create a magnetic field. When charged particles move in a straight line, they produce magnetic fields around them. For charges moving in the opposite direction, the magnetic field will also be opposite. This can be easily explained by the right-hand rule. Point your right-hand thumb along the flow of current, then curl your fingers as if wrapping around the wire. The direction your fingers point is the direction of the magnetic field created by the current. During the 19th century, the only source of electricity was the battery, but the demand for electricity was enormous. Scientists had to find a way to produce electricity other than by using batteries. Faraday worked on this problem. He asked himself if electricity could produce magnetism. Why couldn't magnetism produce electricity? After years of work, he succeeded in 1831. When a coil of wire is connected to a current meter and a magnet is moved inside the coil, the needle on the meter deflects. When a magnet moves forward, electrons start moving. When the magnet moves backward, electrons start moving in the opposite direction. A changing magnetic field causes electrons to move in different directions. If we place a light bulb, we can see that the bulb starts glowing because the moving electrons create electricity. This indicates that a changing magnetic field produces a changing electric field. With this discovery, we later created generators, which are used to produce electricity. Generators are simple. When we rotate, a magnet changes in its direction, produce electricity. Thus, a charge will produce a magnetic field, but only if it's moving. A magnetic field will produce a current, but only if it's changing. A moving charge produces a magnetic field, But what happens if the moving charge suddenly changes direction? What happens when a charge accelerates? Acceleration means an object changes its speed or direction. A charged particle can vibrate, which means it continuously changes direction. And vibration implies acceleration. Let's observe the vibration in slow motion. First, the charge moves upward, creating a clockwise magnetic field around the charge. Then the charge moves downward, creating a counterclockwise magnetic field. This happens very quickly. So the magnetic field around the charge also changes rapidly.
Create a vision where sight becomes story.
See better, shoot better, create better.
You got the camera. Now get the vision.
Electrons are negatively charged particles. When they vibrate, they disturb the surrounding electric field. This oscillating electric field generates a magnetic field at right angles. And here's the truly elegant part. This changing magnetic field then generates another electric field, and so on. This continuous self-sustaining dance between perpendicular electric and magnetic fields allows the disturbance to propagate through space as an electromagnetic wave. Together, these perpendicular fields sustain each other and create an electromagnetic wave. Imagine shaking a rope up and down. The motion creates ripples that move forward. That's how electrons create light. Similarly, a magnetic field is a region around a magnet or a moving electric charge where magnetic forces are exerted. Magnetic field lines illustrate the direction and strength of this force. In an electromagnetic wave, the magnetic field is always perpendicular to the electric field, and both are perpendicular to the direction the wave is traveling. This elegant, orthogonal relationship is what allows light to travel efficiently through the vacuum of space. This mutual generation, an oscillating electric field generating a magnetic field, and that magnetic field generating an electric field, is key. It means electromagnetic waves don't need a medium to travel, unlike sound waves which need air or water. This is why light from the sun can reach us across the vast emptiness of space.
Light does not need a material to travel, and that is why it is even faster than sound, as we are going to see and apply in our photography, videography, and cinematography. Demonstration of fields. A balloon rubbed on your hair can pick up an electric charge, and when you place the electric charge to paper bits, it attracts paper bits. That's the electric field in action. Sprinkle iron filings around a magnet and tap it. You'll see curved patterns appear. That's the magnetic field lines visualized. These are invisible, yet they govern how light travels. What's the relevance to photography? The very sensors inside our camera depend on electric fields to collect charges. When photons of light hit the sensor. Now, magnetic fields are used in motors that drive autofocus systems and in stabilizers like our gimbal. I'm going to show you a gimbal here. So, in our gimbal, we have magnetic fields operating. The same with our lenses. They help the movement of the gimbals and also the movement of the lens component to autofocus. Without electromagnetic principles, modern photography equipment simply wouldn't exist. So what have we said so far? Electrons vibrating in fields are the hidden orchestra behind every beam of light you capture with your capturing devices. Your camera, and you know we have different kinds of camera. The one for photography, the ones for videography, the ones for security surveillance.
Create a vision where sight becomes story.
See better, shoot better, create better.
You got the camera. Now get the vision.
Magnet. So I'm going to place it here. Can you observe what is happening? If you watch very closely, you discover that the ion filings have directed themselves. Some are going to the North Pole, some are coming out of the South Pole. Just look at how it is. So this is very, very interesting. So if I keep doing this, they keep aligning and aligning. Just look at it. Just look at this. Just look at this. Just look at this. Just look at this. Just look at what is happening. Can you see the lines? Can you see the lines? Can you see the lines? So this is a pole. So these are the field lines of the magnet. You see? Some going to the North Pole, some coming out from the South Pole or from the... So this is exactly what we mean. Happening. You can see what is really happening. Let's stop. You see how they are lined at the middle, and then you see how they are lined also at the edges.
Create a vision where sight becomes story.
See better, shoot better, create better.
You got the camera. Now get the vision.
Let's visualize what happens when an electric charge moves. And so on my decks, I have here 3 sets of batteries. Now these batteries contains charges, and I want the charges to flow along the wire. So this is the circuit here. So I'm going to close the circuit quickly and see what happens to this magnetic compass. So we have a magnetic compass, and you see the wire is passed along the north-south pole of the indicator. Let's see what happens when a charge flows along the wire. So I'm going to do this quickly and let's see the effect. So I'm going to close the circuit very quickly. Did you see that? It's telling you that when charges move, that a magnetic field is produced. It's only a magnet that can move a compass. And that is why the compass is used to get direction based on the magnetic power of the earth, the magnetic force of the earth. Now, I'm going to do that again. Can you see the compass move? I'm going to do that fast. Can you see the movement? Can you see the movement? So this is what we mean when we say that when a charge disturbs its electric field, that a magnetic force or a magnetic field is produced. And I've given you a vivid illustration to demonstrate this. You wonder what happens to your autofocus on your lenses. This is exactly what happens. So when it senses an image, the motors move based on the magnet on your lens. So I'm going to change the polarity of the battery, and we'll see the effect on the compass. So I'm going to take off the negative terminal and take off the positive terminal, and I'm going to switch them this way. So I'll put the positive terminal here, and then I'll put the negative terminal here, and again I'm going to align everything to the north-south line of the compass. So I'm going to let the compass settle. I'm going to let the compass settle because it's shaky right now. So once it's settled, I'm going to make sure the wire is well aligned to the direction of the pole. So having done this, the next thing we are going to do is to try to switch this, and we'll see the impact on the compass. What do I expect to see? I expect to see the compass move in the other direction. In the first experiment, it moved to the left. So we're expecting it to move to the right, because the charge, instead of going forward, the charge is going backwards this time around. So let's see this effect on this magnet. And so I'm going to put on the switch right now. You can see it moves to the right. Amazing, amazing, truly amazing. We're going to try this one more time again. I'm going to put on the switch. Just make sure that the compass is steady. So I'm going to quickly put on the switch. Can you see that movement? Can you see that movement? I'll do that again very fast. You can see it moves to the right. It moves clockwise to the right. Now we can see that depending on the movement of an electron charge, either left or right, it affects the formation of the magnetic field and the direction in which the magnetic field moves. So with this experiment, we can establish the fact that when a charge moves, that it generates electric current. That is how we see electric field. That is how we see the bulb comes up. But apart from the bulb coming up, it also generates a magnetic field that affects the magnetic compass and makes it to move or to change direction. We've seen a charge move, and you've seen a moving charge create an electric field that causes electric power, and it creates a magnetic field that causes a magnetic power, a force. Lenses are built with magnet inside of them. So this magnet helps in our autofocus. Let us see what happens when I take this lens close to the magnetic compass. Let's see what happens. If there's a magnet in here, it means something is going to happen to the compass. Right now, as we can see, the compass is very steady. I'm going to move my lens close to it. Can you see what is happening? So this tells you that our lenses are built with magnet.
where sight becomes story.
See better, shoot better, create better.
You got the camera, now get the vision.
Hello folks, my name is Michael Tasker. We're still on the topic electromagnetic wave and the visual arts. How light is created, how light propagates, how light behaves, how with this understanding we're able to control light, to sculpture light and make it fit what we desire it to be, and see the relevance to photography. Now we're going to be doing another experiment that illustrates the fact that when a charged particle moves, oscillates, or vibrates, it produces around it a disturbance, which is the electric field. And in turn, the electric field produces a magnetic field. And in turn, the magnetic field produces an electric field. And the electric field produces a magnetic field. This dance, we know, propagates through space. And this is how electromagnetic waves are carried along, how they propagate, how they move, for which light is one. Yes, light is an electromagnetic wave. And so let us look again at the creation. Let us look at the evidence that a charge is related to electric field and an electric field is related to a magnetic field, and both of them form the electromagnetic waves. So on the table I have an ammeter, I have a potentiometer, I have a switch, and I have a set of batteries, 3 batteries in series, and I also have a coil. Now we are going to bridge the switch. When we bridge the switch, we expect electricity to flow because the charges in the battery will begin to move. As the battery moves, there will be electricity. How do we know that there is electricity? We will discover that the ammeter, which is in position 0, as you can see, it's on 0 right there, is going to move either to the left or to the right, depending on the polarity or the direction the charge is moving within the circuit. And when it moves, it's going to come to the coil. And as you're going to see, when the electric charges move through this coil, it's going to be turned into a magnetic force, a magnetic field. So the coil enables us to bring out more of the magnetic field in a circuit. So what I'm going to do now is to place a compass close to, as you can see, the coil. And then we're going to see what happens to the compass. If magnetic field is produced, we expect that the compass should move. There should be a force on the compass if truly the electric field produces an associated magnetic field. And so right now I'm going to close the circuit. Watch closely. Wow, you can see the ammeter moves to 1 ampere, and then you could have seen that the compass also moved. I'm going to discharge it. You see the compass goes back to its position. Now I'm going to try that again. I just watch closely as I bridge the circuit. Wow, the compass moves. It means the electric charge which produce electric field. The electric field has produced a magnetic field that has caused the compass to move. I'll try that again. Together, the electric and magnetic field creates the electromagnetic wave. This is what we are saying. These things are invisible, but with these meters, we're able to see what happens. Because truly, the only part of the electromagnetic wave that our eyes can see is light. And we are going to talk more about that. And we're going to talk about the implication of this experiment. Now, one other thing you will realize is that this potentiometer, if I take it and move it close to the beginning and I do this, if you check the ammeter, it doesn't get up to 1. It means the current is not as large as. I'll take it off. If I push the potentiometer close to the other end, as you can see, and I close the switch. Whoa, that was too much. That was just too much. That was too much. I'll do it again. Whoops. If you look at the ammeter is at the extreme, and then you can see the kind of magnetic force that is exerted on the magnetic compass. So this brings us to the end of this experiment. Let's discuss about our findings.